Hello everyone. In this video, we'll walk through a complete demonstration of linear regression in Python. I'll cover three main topics. Uh, first, creation of a synthetic data set for the model, and second, implementing the model in Python. So, interpretation of each output term in detail. So I'll cover these three in this video. I hope that at the end of the video, this you should be able to understand not just how to run a linear regression model, but also interpret the output results. So yeah, let's start. Uh, we'll create. Let's just import all the required libraries. Import num was pandas, matplotlib, pyplotus, cfon, linear regression, import Statsmodels, PISSM, numpy, pandas, matplot, scikit-learn, cfon, Statsmodel, and Statsmodel. Now let's create a model. Oh, sorry, data set. Creating a random data set. Here I'm creating a random data set. Otherwise, you can create, if you have your own data set, you can directly import that and run the model. Let's set field. It just ensures that every time you run the same number of like uh, same data set is used. Numbers won't change. So you can here 42. In the place of 42, you can give any other number also. Now let's generate our independent variable. Hundred one. This does it creates 100 samples between 0 and 10. Create a linear relationship with some noise. Now, why I'm doing this is so if you know linear relationship of your data set, it will help us to verify if our model, whatever we are doing, is working correctly or not. That's why I'm defining a relationship. So this is the relationship I'm giving. X plus 5 plus 7 mods. Right. So let's create y is equal to multiplied by x, and I'm giving a normal is distribution. Now let's create our data frame at visualization. Frame and this creates our data frame. Let's visualize the data set. Now here the Gemini AI is giving you don't have to rewrite code also, just know how to do it. This is a data set. On x-axis we plotted if independent and on y-axis we plotted dependent variable. It is following a normal distribution. Let's see or review. This is our like head of the data set. Like this is not the complete data set. We're just taking some values. So now we created a data set with 100 points, and the relationship follows the formula that we defined here. Y is equal to 2x plus 5 plus some random numbers. Now the true coefficient is 2, and the true intercept coefficient is 2, and intercept is 5. Let's see if our regression model can recover these values that like the model we do should give these values of coefficient and intercept. Now let's run the regression. Mm, for this, we will to fit a linear uh, regression model to our data. We'll use two popular Python libraries. Mm, One is Scikit-learn. This is for quick implementation. The second one is Statsmodels for a more detailed output, more detailed statistical output. These two are the libraries, the popular libraries. Let's start with Scikit-learn. Model sklearn dot fit. We are fitting it for dependent and independent variable. So our independent is X, independent is Y. Let's make some predictions. I pred sklearn is equal to model sklearn predict X. Let's just do the scikit-learn stack model view later. Let's print the efficiency. Here is scikit-learn model value. Coefficient and intercept already is giving. Let's take it till 2 points. Similarly here, let's print our R square also. And print mean squared errors. Mean squared error. Yes. Now this will give us the uh, predictions for the I mean using the scikit-learn model library. Yeah. So now our intercept is 5.2 and uh, coefficient is 1.9. R squared is 0.97. Mean squared error is 0.806. I will explain everything like once we are done with the implementation. So these are actually intercept. Our intercept and coefficient are um, you know approximately equal to our assume the values we gave earlier 5 and 2. If we remove this and see how it gives, Or let's just use one. Let's keep it full. Now let's run this with using stats models. Using stats models. Here it will give us a more detailed output than the scikit model. So we will first add a constant. The Gemini is already giving us the code. So we are adding constant, and then the model where OL is ordinary, we are putting OLS model, ordinary least squares regression model for data. And then we are printing the output stats model results and model summary. Right. So why we are adding constant here? It stats model doesn't add constant automatically by default, so we are adding a constant. So this is the output. Dependent variable y, model OLS, method is squares, the date, time, observations, data residuals, model covariance, R square, adjust R square, F stats, probability, with stats, log likelihood, ASD, BIC, all other stats are there. Now let's visualize our results. Also, figure fix regression. Let's add a bit also here. Line let's give a title, any regression field, X label independent variable, Y label dependent variable, by giving the legend, create and show. Right. Now these are the blue dots are our data points that we already saw earlier, and the red line is our regression fit line. It is coming like almost perfectly fitting the data. Mhm. So let's interpret the result here. The coefficient is here. Coefficient here. This is the coefficient 1.9, but it is approximately 2. So this tells us that for each unit increasing x independent variable, write it here. So now we have coefficient which is slope. This tells us each unit increase in x independent variable y increases by approximately 2 units. Or now this coefficient matches our true value of 2 in the data generation process. If you remember the data generation process, we gave a coefficient of 2 here. So it is approximately equal to the coefficient that our model is uh, giving out is approximately 2, right? Um, Next, intercept. This is the expected value of y when x equals, say, expected value of y dependent variable when x is equal to 0. In in our case, it is 5, approximately equal to the phone intercept given by the mode. So here the intercept is this constant 5.21. Now and next r square and adjusted r square. Where is it? Yes, here r square and adjusted r square we are getting 0.976. Both are equal. So r square and adjusted r square. Both are is equal to 0.976. This R square tells us how well the model explains the variation in the data. An R square of 9 point R value, an R square of 0.976 means our model is explaining about 97.6% of variation in the dependent variable y. It explains so almost, and the remaining 2.4% variation is due to noise, some random noise or other factors that are not included in the model. There are some other variables that are affecting our independent variable, but we did not consider those for our our model due to various reasons, because of lack of data or can be any other reason. Now, what is adjusted R square? Adjusted R square is similar to R square, but it when you add unnecessary predictors, it it penalizes your model, meaning it reduces. It says that there are more unnecessary variables. You can even refine the model. In our case, both are same. because we only have one predictor or one dependent variable since the values are same. Otherwise, we would be having different values, uh, and it is advisable or suggested to consider adjusted ask query if you are running your real time, real world data on real world data. And based on that, you can refine your model, adding or removing unnecessary independent variables. Next, we have F statistic. Statistic is the value here. Our F statistic is 40 and row F statistic is this much 1.35 into 10 to the power of minus 81. Now, what do these tell? F statistic says the overall significance of the regression. The high value, like in our case 4000, suggests the model is statistically significant. And the p-value associated with this, now this is our p-value. P-value associated with our F statistic is very small. Now this indicates our model is statistically significant at any reasonable significance value. Right. So this is p-value. So p-value says that our model is statistically significant. Now let's see our coefficients table. Here the coefficient is the estimated coefficient value. This is slope for x1 and intercept is for constant. This is our constant 5, the one we gave earlier, and it is approximately 2, the slope we gave earlier. And standard error of the it is standard error of the coefficient estimate. Uh, For the estimates we have constant slope and constant. These are the standard errors, and the smaller values indicate more precise estimates. Then we have t. This is t statistic for the coefficients that we estimated. Um, so the t statistic testing whether the coefficient is significantly different from zero, and this is the associated p-value for the t statistic, which is less than 0.05, which indicates we have statistically significant coefficient, and we have this 0.025, 0.975. These are the 95% confidence interval for the coefficient. If this interval doesn't contain zero, the coefficient is statistically significant at 5%. Now we have other statistics also, other diagnostic statistics. Here we have omnibus. Omnibus, and it tests the normality of residuals. So non-significant p-value suggests residuals are normally distributed. So we have a non-significant p-value. These are the p-values. So it will see if our residuals are normally distributed or not. And here omnibus means will say that our residuals are normally distributed. And we have Darwin-Watson. This tests for autocorrelation in residuals. So value for us uh, that we have value near close to 2, which suggests that we don't have any correlation in our model. There is no autocorrelation. And same is with JB. JB is also for um, this normality of residuals. And we have skewness and kurtosis. So measures of the distribution of uh, shape of residuals. So skewness, what skewness and kurtosis I've explained in my other videos. You can check those if you don't know. And so the ideal values are skewness should be close to 0 and kurtosis should be close to 3 for a normal distribution, which we are achieving here. Since the data set is we generated is normal, so these are the ideal values that we are getting. Now we'll see residuals also. Then we'll do a small residual analysis. What residuals are, maybe if you can want to know, please leave it in comment. I will do a video on residuals also. Let's do residual analysis. Residuals is equal to, let's do histogram of the residuals. Residuals. Let's do on tables. And here is transparency. So let's give blue only, and let's give a edge color black. Let's give a title. These are residuals. And let's do residuals versus filtered plot. Residuals can form. Let's do give a title. Level filtered values. Yes. Now this gives us a plot on residuals versus weighted values. These are the residuals in the weighted values. And about QQ plot for normality check. Size, store, stats, or black residuals for smooth. Now this shows the residual on our Q plot. So the thing why we did residual analysis is to check our model assumptions. First one is the histogram should be roughly balanced. Like we should have a normal distribution. We're getting a roughly normal distribution, so that is there. So there should not be, and this is for checking homoscedasticity. It is like it should not follow any pattern. And our, our plot also not following any pattern. So it's following homoscedasticity. And the normality of residuals perfectly falling on the normal line. So it is a straight line. So the residuals are following a normal distribution. So this is how like we can say our model is following the assumptions. Now, yeah. So in this video, we learn how to create a data set with a known linear relationship. Created a data set here, and we applied linear regression using scikit-learn and Statsmodel. Scikit-learn gives us a quick implementation, and Statsmodel gives us detailed output. Now, then we interpreted the output, each and every term, including coefficients, statistical significance, and all the other diagnostic measures. And then we analyze the residuals. Uh, these are the residuals to check our model assumptions. So now, like, you have to remember that interpreting regression output requires understanding of both statistical significance and the practical significance of your findings. Uh, while a coefficient might be statistically significant, you should always consider whether its magnitude is meaningful in your specific context or not. Should not be like coefficient is significant, so you should keep that in the analysis or not. It should be like, do you need that coefficient or not? It's the analysis should be going in the direction that what you want, not just what the model is throwing at you. So, and the data set, I created a data set here. Maybe you can use your own data set and check everything. And I placed a link to this code also in the description. You can check that out. Yeah, thanks for watching. And if you have any questions, suggestions, you can leave them in the comments below.